All right. So if we have and are ready for starting, I don't want to kind of hold you back. It's our third training session now that we encounter within our Planets project. And I will just very shortly recap what we had so far and give a little bit prepare a little bit the stage for the trainers of today. And since we have already looked a little bit into SSbD scoping in our first training, which we did online together with Carla and a couple of other colleagues, and the Tier 1 training, which we did actually during the on-site science tour, on-site meeting in Steinbacher, Tirol, and record for you guys. We are now proceeding with the Tier 2 and 3 assessments and get a little bit more slowly into this kind of assessment strategies. But since we are in Poland, we thought at QSAR Lab that we would like to focus really on QSAR. It's a kind of methodology involving many different tools and approaches. So it's, I guess, a good idea that we focus as much as possible here, where we can expect also maybe a little bit contribution from different experts that it's maybe more difficult to fly out. So here we have more access to people, I guess.
And finally, officially welcome you, guys. Yeah, I'm very happy that we managed to organize this meeting here. And I would like to talk about QSARs and computational modeling. So we thought that it would be nice to have some small training here. And this part is divided into two. The first one will be a short introduction to QSAR, how we can develop the model, what is important, how to assess the model. I will talk about it, and also how to apply available models which are in literature or in other open source software. And then we will go to short exercise, and where you will see how to apply available QSARs, what to do, what you can do, how to predict, what is needed at the beginning of the predictions, and how to assess the reports from the open source tools, which you can easily go through. Okay, so quantitative structure-activity relationship models. It is a computational approach that allows for predicting missing values, missing endpoints. Here we can predict activity, toxicity, physicochemical properties, functionality. This means endpoint. And what we have to have as an input to QSARs, we have to create a set of chemical compounds which are more or less similar to each other, and we have to define their structure. And this the finding of the structure in a numerical way, we called that we calculate the molecular descriptors. And besides the structure of our chemicals, we need also for those chemicals measured experimental values for activity or for physicochemical property. It depends on what we would like to model. And then using those two, let's say, sets, we can apply various machine learning methods for calculating at the end the final mathematical equation that relate the structure of our set of compounds with the modeled variable, with the activity or physicochemical property. And from this formula, at the end, we can use this formula to predict this activity or physicochemical property for compounds for which we don't have experimental values. For what purpose do we use QSAR and QSPR models? For predicting missing activity, so for filling the database, but also for searching structural features that affect the model activity. So here we can deliver the mechanistic interpretation of the activity, mechanistic context. So what is important in the structure of compounds, what affects this activity. QSAR models can be applied for different approaches, for toxicity assessment of compounds, for mobility assessment. More advanced models could be used for fate and transport modeling of compounds. We can use QSAR for virtual screening of compounds on one hand, for screening compounds with desired property, but also we can combine different models to screen compounds that will be safe for the environment and for humans. We can use the QSAR also for modeling the pharmacokinetic properties, and also in designing new materials, including nanomaterials and innovative advanced materials. And today I would like to show you what is needed in the development of QSAR models, and we will go to example of application of existing QSAR models. Okay, so in case of QSAR models, there are some rules that everyone should follow. Those rules were established in 2004. There are OECD established agreed principles for validation of QSAR models. And then in 2007, guidance document how to describe such a developed QSAR model was published. And we have to follow 5 rules. First one is defined endpoints. So we have to, for modeling, we have to have reliable data and the endpoint for the endpoint, and the endpoint in case of course, regulatory purposes, it should be important so it should be included in the regulatory. Then we have an analingus algorithm, so it means that each step of modeling should be described in such way that the model should be easily recreated. And the predictions could be performed in an easy way. Then, if we have a model, we have to define applicability of domains. So this is the space where a model works correctly and gives us the reliable results. Also important thing, there are different measures of goodness of fit, robustness, and predictivity that should be calculated, interpreted, assessed, and interpreted in case of model development. And if possible, the mechanistic interpretation should also be given in such a approach. In 2023, a new guideline was published on QSARs, and this guideline covers more holistic approach, let's say, and besides those 5 principles, it also here also those QSARs assessments is linking to SSbD approach, AOPs, IATAs, so how to use QSARs in case of, let's say, new other approaches that are created for regulatory purposes. Okay, so how to develop the model? We have three steps: model calibration, validation, and application. First step, model calibration. So here we, in fact, develop the model, develop the equation. We have to remember that the output of any model cannot be better in quality than the input. So the most important part in modeling, this is the data test. We have different sources of data. We have scientific publications, reports, different databases containing various endpoints for different compounds, and also internal experimental studies. And what is crucial that we have to remember that in case of collecting the data from different sources, there is a need to evaluate this data. So each value should be verified if the measurements were performed correctly according to the OECD test or any other guidelines, and only those only this data that are in your opinion are high quality, they can be taken to modeling part. And where we have a data set, we have to split this data set into, so we have training set, train split, sorry. This is our data set. So we have compounds with measured experimental values. And this set should be split to training set and validation set, training for calibrating the model, and validation set. On this set, we are performing evaluation of the model. There are different methods of splitting, but we don't have time to go through them. Just what you need to know that the training set contains 75% of the data for all of our set. And we have also test set, and here we have compounds for which we don't have experimental values, and we would like to develop model for prediction of those compounds. Beside the data as an input, we need also the structure characterization of the compounds. This we call the descriptors. We have two sources of descriptors. There are, for example, experimental values, experimental descriptors. So here we could have experimentally determined properties like water solubility and water partition coefficient and other properties. And also we have theoretical descriptors, which are calculated from formula, from structure of the compounds, and also from the three-dimensional model of the molecule. So after the geometry optimization of the structure. There are different levels also of complexity of the descriptors. We have zero-dimensional descriptors. There are simply molecular weight or number of atoms. One-dimensional descriptors where we have number of groups. Two-dimensional descriptors, which indicates the connection between atoms and between groups. And three and four-dimensional descriptors, there are higher descriptors which are calculated after the optimization of the chemical structure. So we have a set of calculated descriptors for our chemicals, and we have experimental values which are good quality. So we can go to the other step where we actually develop the model. I didn't say that in case of descriptors, we can calculate more than 5,000 descriptors. And of course, there are not all of them are important and may affect our activity. So the first step in this developing of the model part is the selection of the descriptors. And here we have two options. Sometimes we know what is the mechanism of the toxicity, what is important, which groups are correlated with this activity, for example, which structural groups of chemicals. And in this case, we can arbitrarily select the descriptors to our modeling. But sometimes, very often, we don't know what is the mechanism, and we actually use these QSAR modelings to derive the interpretation of the activity. So in this case, we can use various algorithms and statistical approaches to select the most optimal combination of the descriptors for our modeling. And then when we have selected descriptors, we can apply various methods for modeling. And here it depends on, so the selection of the proper method depends also on the type of the data. Where we have quantitative data, we can use various regression models and partial loss squares. In case of qualitative data, we have qualitative methods like k-nearest neighbors or classification or regression tree methods. And here, just an example of equation, very simple equation. So Y is the model, our model variable. X is there are representative variable descriptors, and during the development of the model, we have to calculate also other coefficients, and then it is easy to only what you need to apply the model. You need only the calculated descriptors as an input to model, and then you can predict the Y value. Okay, so we have the equation, and then we have to move to another step, which is model validation. Here we have two approaches, which both of them should be performed. In case of internal validation, we have to verify whether this relationship described by the model is not a coincidence, and if the contribution of individual chemical of the contribution of the individual chemical to the model to the model's equation is similar, and this is performed on the training set. Then we have also external validation. And in this step, we would like to verify how the values calculated with the model correlates with experimental values. So we only calculate, use the descriptors and calculate values applying our equation, and then try to correlate how the experimental and calculated value. And this step is performed on the validation step. And there are different parameters that should be calculated, assessed, and interpreted during the QSAR development of the QSAR models. Those parameters characterize goodness of fit, robustness, and predictive capability of QSAR models. There are a list of parameters which should be calculated in case of model calibration, model internal validation, and external validation. There are also thresholds where we know that this model is statistically correct. And of course, in case of in vitro of model in vitro data and in vivo data, those thresholds are different. And we we developed the model, we verify, so we validate it, we calculate each parameter that should be assessed, and at the end we have to define the applicability domain. So this is the space, theoretical area of feature So the space of the compounds in which models predicts correctly. So just an example. Here, those green dots that are here, those are predictions within the applicability domain, and the red one that are outside. They may be extrapolated, but sometimes this extrapolation is good, and we only need to verify it next to check experimentally if those if this values of this activity was really at that level. Okay, so always everyone who developed the model should remember that those rules have to be fulfilled by the model, and at the end, now each developed model, QSAR model, has to be described in one way. This is a QMRF. QSAR model reporting format where there are all information containing the development of the model. So what is the developer, what is the endpoint, why this model was developed. And then there are different sections which are where each has to describe the how this model fulfill each of the set OECD principles. And only such models which have QMRF and this information is verified and evaluated can be used for example, for predicting in case of regulatory proposals. Okay, so now you know everything. And how to apply available models. So we have compounds with unknown activity. What we have to do is to calculate the descriptors which were used in the equation, and then you have to predict and assess the predictions. So in case of performing the predictions, some expertise of machine learning methods is needed. And in case of assessment, there are rules, guidance, also which should be those guidelines. This is the help to assess the models. Where can we find QSAR models? Of course, in the literature, there are a lot of such papers containing different QSARs with different methods, let's say. But we always have to remember that in case of literature models, if we would like to apply it, we have to evaluate the model first. In case of OECD principles, if this model is okay, so is reliable, if it predicts correctly. But also, what you need to do is the critical evaluation of the endpoint. So you have to verify if this modeled activity is really your effect. So what you would like to predict, which effect you would like to predict. And then you have to know, you have to assess the data from the training set if they were reliable, and you have to know if this model will work correctly for your compound. So here you have to verify if in the training set there are similar compounds to your. And what you need to do, as I said, is the calculation of the descriptors which were used in the model, recreate the model and try to predict. So here the expert knowledge for machine learning is is needed. And then you have to assess the results, see if your compound, your predictions are in applicability domain of the model, and you have the results. But besides the literature, there are also software tools that you can use. Those software have implemented QSAR models, and you don't need to have expertise in the machine learning method. You just have to select the model. So this endpoint, you have to check if this model covered your endpoint. Then you introduce the input normally as a cast number or smiles notation, or in some of those tools you can draw your chemical. Then this tool itself predicts for you and gives you the report. And here, this is the most crucial point. You have to critical assess the prediction. So here you have to know the rules for assessment of the applicability domain, of also the assessment of the developed models, and you have the results. There are also some, let's say, platforms. There are no open source tools. They works more like cooperation between clients and ELASA or INSTEM. But of course, those tools, ELASA, for example, and Direct Nexus, this is a tool that is also introduced in many OECD guidelines, so it could be also used, but they are not open source. And here also, what actions should be done? Selection of the proper tool, input. You have to give the input. Prediction is performing within this platform, and you have to critical assess the predictions. Also, QSAR Lab has developed one tool, that's a framework, where we can implement various models, literature models, for example. If someone would like to apply such a model but don't know how to perform the prediction, we can implement such a literature model to our framework, and then a user can easily predict the values. And also this framework is of course we can develop model from the beginning and implement it to the client. If you would like to see during the lunch, Carolina and Marta, we have a computer in the coffee, let's say, lunch area, and if you would like, they can show you how not only this tool but other tools are working. So maybe you can try it with them on the computer. Okay, so now we are going to the more exercise part, but just want to show you how those tools really really works. And the first one is EPI Suite. I think that you know it, but just in case, this is the website tool. And now what we have to do for performing the prediction is only introduce our chemical of interest. In case here we have to introduce cast name or smiles, and the program calculate every endpoint, applying each model which is implemented in the tool. So this tool gives you a report from each of predictions. We have EPI suite is only can be only used for predicting physicochemical properties, not toxicity. And this is an example of the report. What you have to check is if this is really your compound. Here you have predictions in case of, so here you have estimated value of the model. In case sometimes when your compound was also used for training the model, so there is available experimental value for this compound for that endpoint. Here you have also experimental values. Yeah, what is very important in each model, in each property, there is a user guide where all model documentation is presented, and also how to assess the applicability domain of the prediction. And in case of applicability domain, in this program, the applicability domain is based mainly on the molecular weight of compounds, but in case of different models, this thresholds, so range of molecular weight for which predictions will be reliable is different. So you have always to verify within this user guide what are the thresholds for your models, and also what is needs to the model descriptors should be verified, but this will be also presented later. The second tool is VIGA QSAR. So just a very short introduction. There are 4 panels in the tool. First, when we have to insert our compound, here the SMILES notation is needed. Also, very important thing that of VIGA, we are not able to predict here any kind of activity or physicochemical properties of the ionic compounds, so only non-ionic could be here studied. And the second panel is the selection of the endpoint of interest. We have different group of endpoints. We have models for human toxicity, for ecotoxicity, fate and distribution, physicochemical parameters, and also human and ecotoxicological PBPK. You can see that in case of here for mutagenicity, we have different models. So usually it is good to tick all of them and see if your compounds if the predictions for any of this model cover your compound. The third panel is how to create the report, if it's in PDF or Excel file. And when you click the predict, program calculates everything and gives you the report. On the first page of the report, we have our structure and predictions. If they are experimental data also for this compound, for our endpoint, they are indicated here. This is the description of our compounds and of all the predictions. Then on the second page, we have a list of similar compounds from which this prediction was performed. So also very important step in assessing, you have to verify if those compounds are really similar to yours. And at the end, we have applicability domain assessment created by program, and there are different let's say, approaches for defining this applicability domain, and program gives you the information if all thresholds which were defined developing these approaches are okay or not, or what you have to do. So what you have to verify if all of those rules were fulfilled, and the and your results, your predicted results, is in applicability domain. And okay, so it was an introduction. You know everything. So now we will try, to do it.
Yeah. So welcome all of you one more time. I hope you would not mind if I will be sitting, because I'm getting a little bit too old for this type of activities, so I will be resting during the training. But let's start with the technical problems. But I will talk you briefly about the aim of the study. So today we will just try to get along how to use two main
We need interaction.
but later. But yeah. Sorry. So today we would just get along with two main tools that are available, which were presented before, and we would focus mostly on API suite today, and I highly encourage you to join the Mural panel if you are available to use your computers. The links should be provided in the chat of the meeting, and if not, you can use your cell phone and scan the QR code. I think they're supposed to be bigger over there, but I think it should work. So within the planners panel,
which one?
Right now, here you have all of them, like a summary, because it goes further in the future. But here we have the mural one. So the whole collaborative platform that we have used on the previous trainings. And if we go to the mural, I see that some of you are already here. We have 3 panels. So the first one is the informational part with the aim of the study.
I think we need more time to.
Yeah, I will just talk through, and because I know that you need time to join everything, and I will just talk. And if we will do exact exercise, I think you will be ready. So.
Okay, so maybe yeah. Here there is Natalia who can help you, and also in case of the online meeting there is Dominika online. So if you have a problem or something you don't know, then please write in chat and Dominika will answer.
Yeah. I just wanted to say that. Yeah. So Dominika would provide also links and answers to questions to the people that are online, and Natalia would be my right hand on the inside. So feel free to ask every one of us, and I hope we will manage to fulfill the second part of the mural panel, which is the big table, AD Assessment Workspace. And here we have 4 compounds, but at first we would focus on the first 2, I think, because we don't have that much time. About the first compound, it's the TCPP. So it's within the work package 4 compound that something broke. But nevertheless, the last part of the mural is the AD assessment rules. So it's like a quick tips how to get along with the applicability domain assessment within the tools. So we can read it and use it to fulfill the table. So that was the introduction to Mural. About the Viga, I think I will skip this part because Anita told you briefly how the tool works. Within this tool, which should be downloaded onto your desktop because it's a desktop application, you could insert molecular compounds in the notation of smiles. You can do it separately or in a batch files, and you choose the models, the endpoints of the desire, and you can obtain the prediction reports. And about the prediction reports, I think we'll do it in a bit, but yeah, we'll do it in a bit. So next one is an API suite. So API suite is is also available as a desktop application, but the newer version is available as a web application. So you can join it via, of course, the links, a link in the lower right corner of the slide, or via the QR code, or also on the bigger screen. It's, I think, the QR code on the right. And that's the main tool that we are going to use today. And the case study of our training is the prediction of bioconcentration factor in fish, in short BCF, for TCPP in short, and adult flame retardants if we will have time. In brief, we can, So, as I told you before, here are all of the QR codes that are needed probably for this short training, but mostly maybe you could just join into pairs or groups. Like one of you would use Mural on your phone if you don't have your computer, and the second one in a group or a pair can use API suite. It's just, to get you along and to get you warmed up before the lunch. So I'll be trying to be like many people in one and read reports and also insert information in the table in the planet. But if you would help me to fulfill the columns in the table, while I will be showing you the Viga report, I will be, of course, thankful for that. So in short, at first we're gonna work on the first compound, which is the DCPP, and in the table we have two sections from Viga and from two sections in which we fill the information from the Viga report and the API suite results. And at the end we're gonna discuss the overall results. So I'm gonna, okay, so we can go through the columns. So of course we would like to insert the predicted BCF value. Then we're gonna assess the applicability domain. It would be just briefly going through all of the criteria that are applied in the report. The bigger, the extended description of the each of the requirements are included in a PDF version of the instruction to this training. It is also available in the folder, which I forgot to mention. So in the meeting section on the Planets platform, we have created the folder for the in silico training, in which we have the step-by-step instruction and the folder with directory with the Viga reports. So that's the materials that we will use. And about the API suite, it was shown before, and we will gonna use it in a moment. So let's go for the first Viga report. in this file. If you need any time for technical problems or do you have any questions right now, we can assist you. But if not, I will just show you the report. And during this this presentation, you can fill the first row in the table. So for the TCPP, we see the structure, and of course, I think it's the proper one. And we have the information that we have the experimental data for this compound, which is a great information because, and also it's information that in the in silico tools, we can not only obtain the predictions or the assessment of some biological or physicochemical activity, but we can export some experimental data that is already included into the software. So, but we have information that the experimental value of BCF is 0.9, but also the model has predicted the value and it is equal to 0.55. In general, the report is saying that gives us an information that the prediction is in a good reliability with the experimental data value. Of course, here we have some basic information about the input that we have used to generate the report. And here is what Anita also presented, the similarity assessment. And as we can see that during the assessment, the software compared our compound to pretty similar, quite a similar compound. So that's another information that we are heading towards positive comeback, which would be a good prediction, a reliable prediction. Moving on, we have the information that are needed to fulfill our table in Mural. So the applicability domain and the measured applicability domain scores. And here we have few of them. And in general, if we would use some different and model some different endpoints, we would have the number of the criteria would vary, and it probably would be smaller than this one. But we wanted to show you the whole extent of the software. So if we have so in total, because we have the experimental value for this compound and the model is the report told us that the prediction is in a good reliability. That means that probably all of the domain scores are saying the information that we are in a safe place and the prediction is reliable. So the global index, so it's just saying that the prediction is in good shape, is in good reliability, and the ADX score index is 1. As we presented before in the report, there are some similar compounds within the training set. So that's why the similarity index is scored as 1. And we can put, okay, I forgot to mention one thing in the planets, that within the first section and the lower part, we have like pictograms that is a green circle with a tick, which tells us that the prediction is reliable. Yellow triangle that says that the prediction is probably reliable, but we need an expertise of an expert to confirm that we can rely on this prediction. And the red circle with a cross, which tells us that the prediction is not good at all, not reliable, and we should not rely on this particular prediction so if we apply the results to the Mural, we can also apply these pictograms to have like a clearer interpretation of results that we are obtaining right now. And moving back to the report, the accuracy index is similar to the compounds that are found in the training set, which is a good information. The concordance for similar structures index is equal to 0.349. And the explanation for this rule is that the similar molecules found in the training set have experimental values that agree with the predicted value. So it's also a great information for us, which tells us that we are going to forward the reliable prediction. Then we have some specific requirements for the log P, for the BCF prediction, which are correlated with the log P. Which are also in a good shape and tells us that the prediction is good. And then we have like the more detailed information about the model, the descriptors that were used, and assessment. So in brief, it's a VIGA report. I know that the whole thing is pretty quick and tough, but I hope it would not cause you a headache, and also because it maybe could be tough. We are here to help you and guide you through next reports that are available in the Planets platform. But before that, before we will go into more independent work, I would also wanted to show you how the API suite works. So we copy the CAS number of our desired chemical. Or something is not working. Okay, it works. Do you see the screen? Yeah. And that's the homepage of EPI Suite web application, which can be accessed via the QR code. Does it work on your cell phones and on your computers? So that's great. I hope it would work because I checked it, but you know, the technical problems are always present. So we paste the CAS number, which is one of the identifiers of our chemical compounds, and we pick the why it does not work? Okay, so let's see if the smiles notation would work. Okay, I was prepared, obviously, for this type of situation. If you paste some identifier into the EPI suite, does it work or not? No. So probably the servers went the high temperature because it works.
Written under chemical?
Yes, with the second one, with the second.
That's the second one. Yeah, I told you that I was prepared. So that's the result window that you will obtain if the application would work. And so as Anita told you before, we have the main window with the identifier and the structure of the compound that we wanted to use. And also we have the information about all of the models that are within that are predicted within the EPI suite. And in case of applicability domain, because right now we have the experimental value, if someone is filling the table within the mural, this is the second compound. So it's the one row below. And for this compound, we also have this is the BCF. But in case of EPI suite, it's important to acknowledge that main endpoint for this tool is the lipophilicity, and based on lipophilicity, the other endpoints are calculated, and also the molecular ranges are involved to assess the domain of the other endpoints. So, moving on to the lower fragments of the page, because you see that a lot of models are available here. We see that the tool predicted the log BCF, logarithm of version of the BCF, and it is equal to 3.87. And how we would define if the prediction is reliable or not, that's where the molecular weight ranges comes into play, and also the descriptors. So we go to the molecular descriptors, and we can see that there's only if we would like to assess the information, what are the ranges of the weight, we need to move to the user guide. I hope it works. And within the user guide, we have a lot of information about the model, how it was developed, on what type of chemical compounds, and what were the methods that were applied to obtain the model. But what we would like to do right now is to see if the predictions are reliable. So that's why we move on just to the domain. Because, as I told you before, the more extended instruction to the solution of the exercise is within the instruction in the Planets platform. And we see that the minimum and maximum range is from 68 grams per mole to 991 for the case of ionic compounds, and around 460 grams per mole for non-ionic compounds. And if we also would assess that the lipophilicity is within the domain, and how we can do it, of course, we compare the molecular ranges within the user guide, but also we can compare the descriptors to see if our compound fits the domain. We need to compare its descriptors with the maximum number value of the descriptor in the training set. So we are comparing the table, the column number to the column training count. As we can see, none of the values exceeds the training count. That's why the logarithm, the lipophilicity predicted is good. So that's one criteria, and the molecular mass of this compound is around 260. So it also fits the range of molecular weight for the log BCF, for the BCF-BAF model. And I know that we are extending time, but how much time I have left?
5 minutes.
Okay. So
Otherwise, lunch will be gone.
okay. So I see that the table is partially filled, and it would not be. I was not expecting that it would be filled in total. But the main idea was to see if the predictions within one tool and another tool is, for the first point, is similar, and it's reliable in both of the tools. So by the end of the day, the table would be fulfilled by me, and it would be for your revision later, of course. But because we don't have time, what we can see that the Vega, which also has around 4 to 5 models for BCF, so we can pick from a quite big variety of models, but I have picked one of them for the sake of the training to not confuse you more. than I already have. The prediction in Vega is 0.55. The ID assessment tells us that it's good. The prediction is reliable. But also the program had shown us that there is an experimental value available. So we agree with the prediction. We would use the experimental value instead of the prediction, but for the sake of the property, we use the predicted. And if we compare it to the, this should be here, I think. Yeah, no problem. And here we have the prediction that's supposed to be, but will it work? But not. But it was around 0.6, I think, or 0.7. Yeah, 0.61. It was 0.61. So if we compare those two values, we see that they are pretty close to each other. And also we assessed that the prediction within the EPI suite is also within the fulfills the requirements to be in applicability domain. And also we have the experimental value from the Vega Hub, and we can compare that they're within the same range of numbers. So in total, we can discuss, we can say that both of the tools can predict highly reliable, can make highly reliable predictions for this compound. And also there is experimental data available for this chemical. And yeah, so as a wrap up for this workshop, we was pretty compressed, but what we would like to give you as a takeaway conclusion is that because in total it's supposed to give you information that other compounds are could not be predicted, or some of them could be predicted good in one tool, and the second tool it would be not reliable. It was like the case of the workshop, but if you would like to use in silico tools, try to compare as many as possible tools and methods to obtain the most comprehensive conclusions. You can collect experimental data from in silico tools, which was shown to you today. And there are some tools that are not versatile because, as Anita mentioned in her lecture, the EPI suite can only be applied to predict physicochemical properties. In Vega Hub, the range of models is more versatile, but you have to remember that not all of the tools can be applied for all of the cases. And obviously, the materials are within the Planets repository. And if you have any questions, we are here to help.